First, I want to thank you all for hanging in there after Alan's wonderful talk, because he let me set up a great intro to my talk, because he talked about all of the background work that had been done through ground-based astronomy before New Horizons got to Pluto and also to Arrokoth. And without the ground-based observations, which would told us that we have nitrogen, an atmosphere, any number of different things, we would not have been successfully able to design, I don't believe, Alan can correct me, but I think that's true, the New Horizons mission as successfully as it was and made it so successful. And this is the topic of my talk. It's synergy in planetary science from the ground up, and I meant that ground-based observational work, in particular, in my case certainly, feeds into the successful space-based observations that we have, which then turn around and inform our ground-based observations, and et cetera. And so, let me see. But first, I would like to thank the AGU for honoring me with the Fred Whipple Award. It's a great honor. I'm honored. I'm stunned. And I'm very, very grateful to all of you. I listed a number of people who have been instrumental in my background here over the years. No person receiving an award, no piece of work is solely due to only the one person. And I certainly have benefited from the input and collaboration and mentoring and support from many people in our field. I'd like to thank them here. And go on from there. So I did want to talk about spectroreflectance work, which is the work that I have been doing over many years. I'd like to start by telling you a story that 45 years ago is roughly the first time I ever made, almost to the day, is roughly the first time I ever made a scientific presentation at a conference. At that time, I had some brand new shiny data about the planet Mercury. We put it on a lantern slide. I was waving the slide to dry before we called the taxi to go to the airport. We ran to the airport, went to the conference. The conference had about 200 people at it, 10 of whom were women. I was a grad student, first talk, and it turned out that the lantern slide was sideways. And of course, there's no real way to put the lantern slide in there, so when they suddenly flopped up, my spectra were all completely 90 degrees off where they should be. Mike Gaffey, who was a postdoc at the time in the research group I was in, walked over, grabbed the lantern slide projector itself, turned it 90 degrees, and allowed it to project so that I could give my talk. And I have to tell you, frankly, that I'm not sure I was more nervous then or if I'm more nervous now about talking. But I do want to put that in. But additionally, I was hooked with spectroreflectance, with any number of different things, but certainly with spectroreflectance work. And that's probably served as the basis of my research over many years, both at the telescope and in the design of different instrumentation. So let me give you a 3-line tutorial as to what a spectroreflectance reflectance spectra is for a rock, in our case. Light will come down upon the surface of the rock, which is made up of these wonderful rock-forming elements, which all have different ions. Most of the light that's reflected off of the surface will just reflect away. Some of it will go interior to that, excite one of those ions to go to a higher energy level, and the light will be absorbed because it kicked something into a higher energy level. That produces an absorption. When we look at the rocks, spectrally, that's a very quick description, but when we look at the rocks spectrally, we see variations in spectral location based upon the structure of the minerals themselves in the rocks. We probably probed only about 1 millimeter in diameter at most. So this is from a paper from Tom McCord in 1972. He pioneered applying this technique to looking at the moon prior to and during the Apollo launches, and he took spectra of the different locations that you could see that are marked there, both that we went to in our Apollo missions and that we didn't go to, and at the time predicted what type of materials would be on the lunar surface. The Apollo missions went to the moon. They got samples from these different locations. They brought them back. We looked at them in the laboratory. Long story short, they roughly matched, and it provides first-order evidence that this technique does work, and we can use it as a probe for the remote sensing of different objects. That was back in the late 60s when Tom was a graduate student. He went on to be a professor. I showed up at his doorstep one day, sort of accidentally, and he encouraged me to join his group because his main interest at the time was instrumentation. And he wanted to design instruments, and he knew I was a pilot, and he figured that I could press levers and push buttons and land a plane and not kill myself. So therefore, he figured I would be a good person to come in and work with his instrumentation and group. And that's how I got my first intense start with planetary sciences. I started working with him as an undergraduate, and I kept going through a portion of my graduate career. But I've concentrated a fair amount on asteroids. And I want to talk about the evidence for the action of water on different asteroids, aqueous alteration, in the visible spectral range. This has been a major portion of my career. It informs a fair amount of what we are doing right now, both in ground-based and space-based observing of primitive or low albedo asteroids. So I've got a variety of different little small topics. I'll break them down and show them to you. But the first is, how do we do this? I've already talked about it a little bit. We look at the remote sensing of mineralogy from ground-based telescopes and some space-based ones that I would call Earth-based, but not up close and personal with the object, but at Earth orbit. We get ground truth. We have meteorite samples which can be contaminated or even should be looked at as possibly contaminated, and we get return spacecraft samples. We've had one spacecraft return samples of a near-Earth asteroid, Itokawa, another one en route back from Ryugu, which is a low albedo asteroid. Another one we know will be probably sampling another low albedo asteroid, Bennu, very shortly. So that's 3 returned spacecraft samples. The minimal, small return from the mission to Itokawa was sufficient to break a paradigm in our understanding of the more processed S-class asteroids. This is going to be worth its weight in gold. It's going to inform us of what it is that we can do. If you get up close and personal with the object, you'll also get some spacecraft elemental compositional experiments that can do very good things for understanding surface composition. So we are going to these near-Earth asteroids, but as of yesterday, yesterday, there are 854,264 asteroids in JPL horizons, of which 541 some odd are numbered. I do not expect that we are going to all go sampling all of these asteroids. I do not expect that we'll sample most of them or visit them, even in my lifetime. Regrettably, actually, I think it would be cool. But Earth-based remote sensing is going to remain our best means of studying a large sample of asteroids, and we should perfect whatever we can in order to be able to study them. So I'm jumping quickly to in the 1980s, an early study of classifications of broadband photometry of asteroids. 589 asteroids were observed through 8 broadband filters. 3 of them I'm emphasizing at the top, the V, the W, and the X, because of their spectral locations. And this is called the 8-color asteroid survey, or ECAS, as I'll call it. Dave Tholand broke them down into reasonable asteroid classes, and I have marked with the red oval low albedo asteroids that look pretty darn flat across most of the visible spectral region, and those are the subject of a lot of my research and what I'll talk about today. As a graduate student, I developed a CCD spectrograph and took higher spectral resolution asteroid spectra of some of these lower albedo asteroids. And when we looked at the higher spectral resolution, we found that the large broadband filters can mask a fair amount of information that's present in these objects. We discovered a large number of visible spectral region absorption features. In the lower right is a feature that is very common, actually, in CM2 carbonaceous chondrites. There are other chondrites. I've plotted here the background of the reflectance divided by the linear continuum for both some of these low albedo asteroids plus some CM2 carbonaceous chondrites to show you some similarities, some differences. But the big one is here. It is centered roughly near 0.7 microns. It's probably due to an Fe2 plus Fe3 plus charge transfer transition in phyllosilicates. We see these in terrestrial phyllosilicates. We see them in CM2 carbonaceous chondrite meteorites. And we see it all over the place in many, not all, but many, C-class or low albedo asteroid spectra. I also noted two other features there. The very small feature near 0.43 microns and the general drop-off that you can see often in the UV blue. This is a spectrum of 19 Fortuna, and I use it as an example of these. We saw other types too. We haven't pursued this as much because these are generally much smaller number and weaker, but there are features that suggest that possibly they have similar compositions to the terrestrial iron oxides hematite, goethite, and iron sulfate jarosite. That hasn't been pursued, but they certainly are there. So with this, we want to take a look at where bound water would be in the solar system, because the phyllosilicates would suggest bound water. And we're back to this image again, and those filters. It turns out, and this is totally serendipitous, that the 8-color asteroid survey had 3 filters at 0.55 microns, 0.701, 0.853, that perfectly encompass the shape of the 0.7 micron feature in the higher asteroids. So what you're seeing here is synthetic 8-color asteroid survey spectra, or survey filters, 1, 2, 3, made from a Gaussian, I modeled it, of these filters, and the spectrum itself, and it obviously delineates where this feature is, and that the feature is there, albeit very faintly. Here's some others. They modeled from low albedo asteroid spectra. Clearly, it's one way that you can find that. So here's the big advantage to that. We have a small number of asteroids that were observed at that time with the CCD reflectance spectra, but the 8-color asteroid survey had 589 asteroids with broadband photometry in it. We were able to search them and test, is it there, is it not there? And largely in the low albedo asteroids itself is where you would find these, and they were pretty much only in the C classes and as defined by Dave Tholen, roughly. We took a look at, this is not corrected, it's not bias corrected for distribution, but just taking a look at the 8-color asteroid survey photometry. Here it is with the percent of asteroids that tested positively versus negatively, and across heliocentric distance, and it's turns out that across from about 2.6 to 3.2 AU, this type of asteroid with this particular feature dominated the main asteroid belt and extended out a little bit further than the main asteroid belt. It's also largely absent in the near-Earth asteroids, or it's maybe not spectrally detectable in the near-Earth asteroids. And how does it correlate with the 3-micron feature that's a water feature that everybody looks at? The most definitive study of that has been done now by Ellen Howell and company. The presence of the 0.7 micron feature always indicates the presence of a 3-micron feature. But the converse is not true. If you have a 3-micron feature, you don't necessarily show the 0.7 micron feature. About 50% of the asteroids show this correlation between the two, and the rest don't. And it's probably simply due to a different compositional makeup. Now, Taki Hiroi did a very good job of taking CM2 carbonaceous chondrite Murchison samples and heating them in steps of 100 degrees centigrade. That's an example of it with the unheated, and you can see the 0.7 micron feature sitting there in the lab sample. But by the time you get to heated, it's gone. You get to 400 degrees, it's gone. If you've heated Murchison, he was looking at more metamorphic creation in rocks, which makes perfectly good sense, but it's gone. And the mineralogy has changed, which would suggest that the last event, that it never gets above a temperature of about 327 degrees C is what he said. So let's take it a little bit to state that on the surface of a solar system body where you see this feature in strength, the last event on that surface of that body that affected it is not going to have gotten to high enough temperatures to have exceeded the point that created those phyllosilicates, or they'd be gone. They would be gone. So you can take this. And first, I'd like to point out, many other people have done studies addressing the presence of the 0.7 micron feature in CCD asteroid spectra. Here are a few. I just want to make this point simply because it's not me. By now, probably a few thousand of these spectra exist, and if you went into the broadband photometry, even more. But There are some. So the point is, we have a tool that we can take and examine the rest of the solar system, basically. We can look for this 0.7 micron feature, and we understand that it has some constraints. And we can take it to the table and say, and here it is, let's try this, let's propose. And what I want to emphasize to people in general is, if you have an idea and you want to, this was important to me when I realized I had this award, if you had an idea and you want to push it forward, take it and push it forward. Don't assume that you cannot do something. Don't assume that what you're looking at, even if it's different from what everybody else is pursuing at the time, is necessarily has no value. And I would like very much for, if you take nothing away from the rest of my talk, please take that away. That's the way science is advanced in all directions, in my opinion. So, okay, so people keep looking for things in near-Earth asteroid. So I have from Eri Tatsumi, who is on the Hayabusa 2 team, as I am peripherally as well. There was a polar region campaign that took place. After she had worked on, actually it was Eri who did it, worked on improving some of the flat fielding that the spacecraft had produced back. And then they went to the poles, and they took a look for different things. They went to an altitude about 500 kilometers. The Ryugu, as an asteroid, is literally just, rotates on an axis that does not vary. It does not have, it's all pretty uniform. The axis is 90 degrees to where the sun is here, that's Ryugu does. It doesn't vary a great deal as far as that goes. Here's a picture of it. The images were binned 8x8. They have a camera system with filters, the ONCT, onboard navigation camera, with 8 filters, which closely match the ECAS filters, including the V, W, and X filters, in order to look for the 0.7 micron feature. It had not been seen until now, and there it is, related to what their camera is. Until now, when Eri has gone back and her team has gone back and taken a good look at the improved photometry and sees that the, if you could see this, the more brown images here, the 0.7 micron feature, show an absorption of about 2.5% that would indicate that the 0.7 micron feature is present. And that was what one of their purposes was to look for that. That's the North Pole, that's the South Pole, same sort of thing. It's showing that it's present at these locations. These are not for distribution, these images yet. They're still, although she's presented this at a conference. They've compared them, the 0.7 micron feature with the same areas with solar flux across the surface at the poles, indicating where it's low and where it's higher. A lower solar flux is seen at the poles in the space weathering, which correlates a little bit better with the 0.7 micron feature than the solar heating, which they also took a look at to see if that might be affecting what the creation or the maintenance of the 0.7 micron feature is there. Remember, we don't see the 0.7 micron feature in very many NEAs at all. We don't really see it at all from ground-based data, even if I said so once, from ground-based data of Ryugu. But it just may be that it's sufficiently subdued for whatever purpose is that we aren't able to discern it spectrally. And we need to get our spacecraft up closer. But I'm pretty pleased with that. Finally, I thought I'd tell you, since I had some hot off the presses data many years ago, that I should show you some hot off the presses data that I'm working on right now. And the motivation for this was to take a look at what we could see in the irregular outer Jovian satellites, because we wanted to take a look at whether violent mixing that has been proposed for the objects in the solar system would predict destructive collisions, and pieces of these objects would be retained in the regolith of stronger asteroids. There are dark inclusions reported in all over types of chondrites all over the place, C1, C2 class. And they're most similar to the CM2 chondrites, CR2 chondrites. And so we were looking for evidence of possibly fragmented KBOs that might be aqueously altered, in other words, spectral markers for the aqueous alteration in red asteroids, red being wavelength, signal increasing with increasing wavelength. And as part of this, we took a look at some broadband photometry years ago, and I'm going to concentrate only on the J6 Himalaya prograde group, Himalaya, Alara, and Lysithea. The broadband photometry, these are faint guys, would indicate largely that they were gray and that the presence of the 0.7 micron feature was there in the broadband photometry. It varies a little bit, maybe getting less strong. What we were looking for when we were doing our analysis was the following: the 0.7 micron feature, 0.43, the UV blue drop-off. What they indicate, the 0.7 micron feature, serpentine and sapphonite discriminators, they would be located differently spectrally depending upon the serpentine, the content in the serpentine, including iron content. Level of reddening might indicate organics. The geometric albedo, which we took from NEOWISE observations so that we had a uniform geometric albedo group to look at, would indicate information about opaics and maybe the level of aqueous alteration depending upon how in-depth you get. And so we also took an approach where we took the brightest object in a cluster and modeled it, and then looked to see what sort of changes occurred when you went to the next brightest object and then down to the next brightest object. The brightest object probably has the best signal-to-noise ratio. There's Himalaya, and we observed it once, Alara twice, and Lysithea once. Those are the change in albedo, bright to less bright to much less bright. And then I will show you, this is my hot off the presses work that we've been doing very recently. We were looking at Himalaya, and we looked at a low iron containing serpentine 115, it's from the Relab, and an amorphous graphite combo that was used as a darkening type of agent as well. It was included in this. This is so far the best match that we have had. We go down to Alara, and we look for two things here that are important. One is that it's beginning to get a little bit redder in one spectrum. Remember that if you looked at the broadband photometry, it was either red or not red. And serpentines, again, low iron serpentine graphites. But you're beginning to see some organics, going from no organics to the presence of organics in Alara, down to Lysithea, which was the smallest, faintest, and the darkest. And the amount of organics has doubled in volume in our models. The amount of it has doubled, and let's see, the serpentines, they're about the same. They've gotten a little bit less as we've gone from Himalaya to Alara, and then down to Lysithea. This is a work in progress, but it's an interesting idea to try to model what arguably could be one original body. Finally, because I liked instrumentation, I fooled around with making a chronograph that was also a spectrograph years ago as a graduate student. And though I produced only spectra for me, it did produce in the lower left-hand corner the first detection of a circumstellar disk around another star, Beta Pictoris, in 1984, done by my graduate advisor for my PhD, Brad Smith, and Rich Terrell. And what is stunning to me is how much things have changed, and I want to point this out. Within that time, of course, it has changed. But chronographs coupled with adaptive optics, now tracing in the right-hand side, using this instrument called Sphere, that's also Beta Pictoris. If the chronograph knocks out the star, the planet itself, if you look at the dates, is moving in its orbit around the star. And it gets to a point where it gets lost in the brightness of the star and come back later from November 2016 to September 2018, and you see it reemerged. So again, I would argue that synergy is an important thing. Ground-based data will inform space-based samples that come back from small satellites and asteroids will inform the ground-based, and we can continue to do our research. And on that, I'd like to again thank the AGU. So.
Thank you so much. Really nice. Thank you, Faith. Do we have questions for Faith?
Did I have way too much time more?
No, you're fine. Yeah? Okay, great.
That's dangerous.
Faith, would you care to make
I would hope that they would find some phyllosilicates in the Ryugu samples that are similar to the CM2 chondrites. I believe we have sampled closer to the equator, where both heating and any sort of solar flux will be great enough that it may have already affected that material that's on the surface at that location. So I'm not sure that we're going to find that, but we will find some really darn interesting things. We always do. Sir?
Will this help us understand how water was delivered to the Earth?
That would be my hope. If in fact bound water is located in all of these different asteroids, and you see a pattern of it across the solar system, or across the main asteroid belt, and also across the solar system, as many other people are showing as well. Yes, I would think so. We can show a straight path into the Earth. Why not? Yes.
Anyone else? All right. In that case, let's thank and congratulate Faith again. Thank you. Thank you all very much. Thank you so much. Well deserved. Right. With this, we're closing this session, and hope to see you at many of the Planetary sessions. And don't forget that we have our Centennial sessions on Wednesday.